Hey guys, how you doing? As some of you I'm sure heard, had a little bit of a run-in with the old COVID-19, but I'm back. I ain't even scared. If you have any questions for me, if you want to know how it went, I don't know, whatever, shoot me an email. Be happy to talk to you guys. I did get pretty sick for just a little while. Got pretty sick pretty quick, but I am on the mend. I ain't even scared. It's a bow tie. He knows where to go. He knows how to do it. But yeah, I'm back. So you know what that means? It's time for learning. So we left off talking about acidic solutions and basic solutions, and like what makes a solution acidic, what makes it basic. If you remember, too many hydrogen ions makes it acidic. Too many hydroxide ions makes it basic, right? I mean, that's really all there is to it. And we went over some of the like characteristics and whatnot of an acidic solution and a basic solution. Acids are sour. Acids are electrolytes. They change indicators' color. The acids react with bases to make salt and water. I'm sure you remember the tune. It was good. Also, acids react. Certain acids. Well, wait. Let me back up there. Acids will react with certain metals. Metals above hydrogen on table J of your handy dandy reference charts. They will react and make hydrogen gas, and they basically just dissolve the metals. If I had all my lab here, it'd be pretty awesome. I could just like melt metals away for you. It's actually pretty cool. Although you kind of saw it. If you remember the coffee can little incident, third period, yours went a little wrong, a little early. But if you remember that, what I did was I poured hydrochloric acid over zinc, and it went and bubbled because zinc on table J is above hydrogen. So I added an acid, and it turned the hydrogen ions into hydrogen gas, which, boom, then go boom. So yeah, so those are a little bit of the basics of the solutions. Now, to say if a substance itself is actually an acid or a base is a little bit tricky because the substance, when it dissolves, interacts with water. And it's really how that substance interacts with water in the dissolving process that helps determine if it's an acid or a base. Because if you take substance, if you take substance and you pour it into a solution and it produces a solution with more hydrogen ions, we call that substance an acid because it's making more hydrogen ions in solution. Same thing, only absolutely completely opposite. If you take a different substance, right over here, if you take a different substance and you pour that into solution and it makes a solution with more hydroxide ions than hydronium ions, then we call that substance base. Are you picking up what I'm putting down? So the real basics of it are, if you take something, put it in water, more hydrogens, acid. Take something else, put it in water, more hydroxides, a base. And wouldn't it be, and that works. That works great. And that's where we were at for a very long time. And wouldn't it be lovely if life were that simple? Right? When have you known this to ever be that simple? Not me yet. So if you all right, so we're going to learn today two ways that we identify or classify a substance as an acid or a base, right? The first is called Arrhenius. That's the name, it's the method named after the dude, and that one's super easy. That's for stuff that dissolves completely. Like it dissolves, it's a one-way reaction, in and done, nothing else. But there's a problem. That problem is equilibrium, because there are some things that we dissolve in water, and instead of a one-way reaction, it's actually a two-way reaction. So it dissolves, it makes ions, and then the ions come back together. It makes ions, the ions come back together. Ions break apart, come back together, break apart, and they come back together. And so what is it? Is it an acid? Is it a base? Like who? It all depends. So once equilibrium comes into the equation, we have to have a different way of naming an acid or a base. And so that's called the Bronsted-Lowry method, named after a dude named Bronston and some other person named Lowry, and they sort of like came up with this at the exact same time, independently, but at the exact same time. So, pitter patter, let's go get at her, guys. Definition of an acid or base. The first one, like I said, the method that we're going to use is super easy. This one, Arrhenius acid. Arrhenius, named after dude Arrhenius. This one is about as simple and sweet as it gets. Plunk it in water. If it makes only hydrogen ions, or hydroniums, because it's a hydrogen ion, it's an H+. but in water. Then we call it, we call it an acid. Super easy, right? That's Arrhenius' method. To name an acid. Now, an Arrhenius base, guess which ion the Arrhenius base makes? Yeah. So acids and bases can come in a couple different varieties or flavors. Monoprotic. So mono, M-O-N-O. What is that? You guys know what that prefix means here, right? Mono is singular, right? Protic. Protons. Guess what that means? Yup, you bet. One. Bing, bang, boom. Only creates one hydrogen, right? That's like HCl, HBr, anything with one hydrogen, right? But not all acids are like that. There are many acids that can actually produce more than one hydrogen when you plop it into water, and that makes them kind of like extra spicy, you know what I mean? Because that's just like with the colligative properties, right? You add one molecule, but you get more than one stuff, you know what I mean? So like phosphoric acid is H3PO4, so you get 3 hydrogens for every one like unit of H3PO4. Do you guys understand what I'm saying? Here, I'll show you. We'll like expand on it. Polyprotic. Harkening back to English class, and like let's not leave Clang Bang upset, because you know what poly means, right? Poly is a prefix that means many. Again, protic for protons. It is a many proton acid. So this acid, you pop it in water, and it makes a whole bunch of hydrogens, or okay, more than one. It depends on how precise you want to be with your language. It's English. Yeah, you're not going to get it for precision from me. So diprotic makes 2, triprotic makes 3, di-tri. These are the prefixes that everybody knows about. Di is 2, tri is 3. And I think that's about as far as we go. I don't actually know of any acids that have 4 protons, although I'm sure there are. There's some sick, nasty acids out there, but we're just going to stick with mono, di, and tri. Okay? So let's check it out. Let's look at HCl right here. So what kind of protic acid is this one, right? See how there's nothing right here? There's nothing there. I got nothing there. That means 1, right? So this is going to be monoprotic. You dig? So that's 1 HCl will give you 1 hydrogen ion. So if you have 1 mole of HCl, how many moles of hydronium ions are you going to get? Yep. This is how it works, right? Pretty easy. So it's like this, it's 1 over here times 1 here, you only get 1. All right, let's go to this next one and see how this one will do. H2SO4. Is this one mono? Is this one di? Or is this one tri? Oh, you're right. This one, H2, right? H2SO4, that is going to be diprotic. Dig? Because there's 2 of them, right? Now, if you have 1 mole of H2SO4, and each mole creates 2 hydrogen ions, how many hydrogen ions do you have in all? 2. Very nice. See, you guys are smarter than you give y'all credit for sometimes. I'm just saying. Moving on. This one right here, H2, it's H2SO4 again, guys. I already know what this one is. I know that this is diprotic. See, because I've got my little like subscript 2 right there, which tells me that for every 1 H2SO4, I will get 2 hydrogens. So let's dig it. I have 1.5 moles of H2SO4. Each mole will make 2 hydrogens. How many hydrogens do I have in all? I'll wait for it. Go on. Remember, I have 1.5 moles. Each one makes 2. How many in all? Well, you're right. You're going to take 1.5 and you're going to multiply it by 2. Right? Junior Bergerac and stuff in my house. Nothing new. Alright, let's do this next one. Phosphoric is one of the only acids that I'm actually like afraid of. This one's nasty. So let's check it out before we dig in. H3 H3PO4, mono, di, or tri. I want you guys to lock into that to see that it is triprotic. You get it? There's a reason why I'm hammering this away. I know you guys are not dumb. You can see whether there's 1, 2, or 3 different like hydrogens coming out of these. My point here for doing this is that I need you to like lock in on the just numbers of hydrogens. It is very important because it affects how these acids behave in chemical reactions for what's coming up next. Are you guys with me on that one? So triprotic, let's go through the way that we think about this. We have 2.5 moles. Each mole makes 3. So how many moles do we have in all? I had a calculator somewhere, man. I don't. Don't judge. Don't judge. 7.5. Lovely. Nice. Ooh, 7.5. You guys good? Nice. Let's clean this up so it's not so nasty. Ooh, sorry. 7.5 moles of hydrogen ions created on that one. You guys see how easy that is with the mono di tri thing? That's important because this H3PO4 is going to behave like triply as acidic as this HCl when it starts reacting with stuff. Got it? Awesome. All right. Arrhenius base. Well, if an Arrhenius acid is an acid that only creates hydrogens, then an Arrhenius base will only create hydroxides when you plop it in water. It seems like ridiculously straightforward when you stop and think about it. You know what I'm saying? All right. Hold on a second here, guys. There we go. Sorry, little technical glitch over here on my end. So look, some of these Arrhenius bases, they work really similar to your Arrhenius acids. You got this NaOH right here, right? Well, how many OHs do you have there? Guys, you got one. You know what I mean? So what happens when we put this NaOH into water, it produces an aqueous sodium ion and it produces an aqueous hydroxide ion. Water doesn't really bond with these. Welcome to my house, guys, man. Yeah. Water doesn't bond with these like it does the hydronium or anything like that. All right. But it like dissolves them and we get sodium and we get hydroxide just like the acids. You see that the sodium hydroxide, each sodium hydroxide has 1 hydroxide. If you have 1.5 sodium hydroxides, how many hydroxide ions in all? Very good. See, I knew you guys could do this. Not super rocket science stuff here. Yeah. Let's move it on. Calcium hydroxide. Now look at this right there. Look at that. Okay, see that? That's just mean. But you're going to see it. It's not that sneaky because I'm really trying to get you guys to dial in on those subscripts. Huge impact. Don't get me worked up, man. I can't handle worked up right now. So look at the subscripts with you. So this stuff right here, calcium hydroxide, makes 2 hydroxides because that's how much it has in the compound. Works just like the diprotic. Has a mono and dihydroxyl or hydroxide, but we don't really worry about those words too much. So if each calcium hydroxide makes 2 hydroxides, and we have 1.3 moles of calcium hydroxides, how many do we have in all? Yeah? Not too, yeah, you guys get what I'm saying. You guys following this. All right. Oh. Well, look at that. Is ammonia. This is ammonia right here. Like the active ingredient in like most of your household cleaners. It's NH3. Do you see any hydroxide in? I don't see any hydroxide in that. Like, not even a little bit. But look, we're calling it a base, which doesn't make sense. But look, this is why. When we take sodium hydroxide and we mix it with water, it actually makes an NH4. Because let me see if I don't know if I can. I'm going to try to be fancy here, so Don't judge me. If you remember, ammonia looks like this when we did our Lewis dot diagrams. I tried to draw ammonia like 1,000 times because I was like, man, you're going to need to know what ammonia looks like. So what's important to see are these two right here, these two what we call unpaired electrons. And remember, that's where they made the coordinate covalent bond when it bumped into a hydrogen ion. Well, look, here's the thing, man. If you take this stuff and you put it in water, it's like, remember, water is always colliding with itself and breaking apart. It makes a hydrogen ion and a hydroxide ion. Well, if you put ammonia in that mix, right here is a place where that hydrogen ion can go, and it does. It lands right in there, does its coordinate covalent bond, and becomes this thing. It becomes NH4. You understand what I'm saying? It becomes the NH4, and it stays there because it's super duper stable, which then leaves a whole bunch of this stuff left over. Which is why when we add NH3, when we add this stuff to solution, I'm gonna kill this now, if you don't mind. When we put this stuff in solution, we actually create more hydroxide ions. Not that we're actually making hydroxide ions, but what's really happening in the water is that the ammonia is gobbling up all those leftover hydrogen ions from the water collisions. So every NH3 gobbles up a hydrogen and becomes NH4 and produces one hydroxide ion. Do you understand what I'm saying there? That's how NH3 is a base. Because when you put it in water, it produces a hydroxide ion, and the solution becomes more basic. You dig what I'm saying? Now, how are you supposed to remember this? It seems crazy. As first year ever taking chemistry to remember all these acids and bases. It's insane. Not fair. It's immoral. It's unethical, and really not even, it's not cool, man. Hold on, man. Let me see if I can find this here. Where could you possibly go? Hey, don't look at that. Look right here. Look right here. Wait, let me see if I can go like this. I'm sure you've already done this. Ooh. Oh, look right there. I didn't even have to type the whole thing in. Let's go on this silly search. Reference table, physical setting. I just found this online. I'm like, I don't even care. Yeah, I'm gonna download it. I'm just gonna look at that. Oh, that's pretty good looking. You see that right there? See that right there where it says common acids? I want to like take a moment here and actually look at this, if I may. This is my version. I just, no excuses, man. It's there. Table K right here lists. Are you scared? You scared? I'm not scared. Yeah, I'm not lying, man. It's a doozy, man. Whew. Table K. If you look at Table K here, I want you to look down the column here, man. You see almost every single acid or base. And by the way, I've seen maybe in my career one acid that wasn't listed on Table K ever that was mentioned on the regions. Otherwise, it was in the reading and it said this acid blah blah blah, and it told you outright that it was an acid. So that table has like all the acids that you're gonna need. Okay, and if you look, pointing at the screen, if you look right, mya and mya and mya and mya and mya and mya and even mya and so not that one. Dude, it's kind of, dude, they all start with H. They all start with hydrogen because that's the ion that they're going to make. That's why they're in there. There are 2 exceptions to the rule, so you're going to see that on the regions this year. They're the ones at the bottom. They're this one, and then this one. This one is pretty important for us. It's called carbonic acid. It's the acid that is formed when carbon dioxide dissolves in water. It's one of the reasons why, like, seltzer water or carbonated water, some people prefer it. It actually changes the flavor of the water because it makes it slightly more acidic. I think it brings it down to like a pH of 5. Yeah, the carbon dioxide basically like just makes more hydrogen ions available. And this is called ethanoic acid, or acetic acid, or vinegar, depending on how you want to call it. It's been around for so long, it has tons of different names. That's why it has like 3 different names. But this right here, do you see the shape where it says COOH right there? That COOH, we're going to talk about that in chapter 11 when we talk about organic molecules. That is the shape or the makeup or like the formation of what we call an organic acid. That's like citric acid, vinegar, vitamin C, DNA, deoxyribonucleic acid, because on the very, very tail of it, it's got this little group right there. And that's why they call it an acid. And what happens is this hydrogen right here, that guy breaks off and goes into solution. So there you go. Right there, all your acids that you're going to need to know. And look, all your bases. And look, I even did everything I highlighted for you. See? These are your bases. These are the ones that you really need to know. And if you notice, ammonia is right there. It's like hitting you in the face with it, man. They really want you to know that ammonia is a base, because ammonia is a really important molecule to life. Like it or not, man, it just is. All right, you guys got it? You guys understand where you can go for stuff? I hope so. I need you to remember, ammonia is a base when you put in water, even though it does not contain a hydroxide ion. You good? Good. All right. So let's have a little thing. And I don't want you to look at your reference table, because you should be able to do this without the help of your reference table. So right quick, this one. See how it has the COOH at the end? A lot of people are like, yeah, but it's got OH, right? So it's got to be a base. No, it is not an OH, because it's an OH ion, and carbon-based things are always covalent. So that, man, it's COOH. You go like this, be like COOH. That spells coo. So you'd be like, coo, man. I know that's an acid. Right? Look, see, acid. I know that. These are known quantities, man. That one, cesium bonded to a hydroxide. We call it cesium hydroxide. I'll give you a minute to think about this one, if that might make a hydroxide ion in solution and become a base. I really hope that was long enough for you. Yeah, because that there is also a base. All right, good. If I got that wrong, I'd be embarrassed. Next one, barium hydroxide. Could it be? Yes. Yes, it is. And finally, H2CO3. There's a carbon in there, so it can't be an acid or base. No. A couple of reasons. I just looked at it at the reference table, right? Because that's where we're going to go to look at everything. Sure enough, it's an acid. Good. Do you guys get this Arrhenius thing? This one's not too terribly complicated. For it to be an Arrhenius acid, you put it in water and it makes a hydrogen ion. That's it. For it to be a base, you put it in water, it makes a hydroxide ion. That is it. You can have monoprotic, you can have diprotic, you can have triprotic. I need you to lock in on that, because that will really start to become important as we move forward with like how these things react chemically. And same thing with the hydroxides. You can have mono, di, or trihydroxyl bases. More important for what's coming next than for where we're at right now. Good? Awesome. All right. So here's the deal. This all worked really well for like the longest time until it didn't. And then we had to rewrite everything because some dude named Le Chatelier, or some silly French dude, broke chemistry with this reversible thing. Everyone thought like, oh, it's crazy, man. Yeah, chemical reactions go one way. I burn a piece of firewood. It's done. Like, actually, no, it can be undone. It's reversible. Depending on how big a system you want to look at. You burn a piece of firewood, makes carbon dioxide, water vapor, and ashes. The ashes go back into the soil. You plant the seed, and then that seed sprouts. It gathers up the nutrients from the ash, takes carbon dioxide from the air, takes water from the ground, builds a new tree. You get what I'm saying? Yeah, so things are reversible, right? Reactions can go forwards, reactions can go backwards, and then when you have an equilibrium, it's kind of a problem. And that's what these dudes discovered. The Bronsted-Lowry acid and base solution is because of equilibrium, man. Because Arrhenius said an acid, you put it in water, makes a hydrogen. But then it goes the other way and it like absorbs a hydrogen. So what if you wrote, one dude wrote the chemical, because it's a back and forth, right? But what if someone wrote the forward reaction going that way, but somebody else wrote that reaction as the forward reaction? You know, like you wrote it out, and for you, the reverse reaction is what someone else was calling the forward reaction. That's stupid because now you're calling it's. They're smarter than me. I wouldn't have been able to figure it out, but they did at the same time. So instead of calling it the Bronsted acid-base theory, we call it the Bronsted-Lowry acid-base thing. All right. So again, it's because of equilibrium. It's because not all chemical reactions go one way and then stop. They go and then they like are reversed, and then it's like it's a constant back and forth, which makes it hard to put a label on something when if 1 minute it's making a hydrogen ion and the next minute it's making the hydrogen ions like be lower, so or the amount of hydrogen ions be lower. It's kind of watch. Oh, it's pretty clear though. So look, first we're gonna name. And then we're going to do a couple examples. So Bronsted-Lowry. So because of this whole equilibrium thing, they're like, all right. It doesn't matter how you write the equation, whether you wrote it this way or that way. Bronsted-Lowry acid is anything that is able to donate a hydrogen ion to solution. Now look, donate. Don't get stuck on this word. The word donate means to give, or to give off a hydrogen, to produce a hydrogen, to add more hydrogens. What are some other words? To lose a hydrogen, to share. Oh, yeah, to share. That's another one. Share a hydrogen, lose a hydrogen, add hydrogens to solution. There's a million different ways to say this. But basically, it loses a hydrogen. It loses one hydrogen into solution, and then we call it an acid. You got it? So if an acid loses a hydrogen, hold on, guess what a base does? You guys are smart. You got it, right? The base, in this case, the base is any substance that is able to accept, absorb. What are some of the good ones? Take, add on, gobble up a hydrogen ion. Does that make sense? I hope so. If not, it will in a few. So the Bronsted-Lowry acid is anything that donates, gives off, produces, or loses a hydrogen ion in solution. And the Bronsted-Lowry base is anything that accepts, absorbs, adds on, gathers up those hydrogen ions in solution. Does that make sense? Maybe, maybe not. All right, so let's look at this little sample that we got right here. Yeah? So look, this is like the equilibrium thing. Now look, I wrote it backwards. Because I can. Like any reversible reaction can be written this way or it can be written that way. It doesn't matter. It's all the same reaction. It's just a matter of how you happen to write it. And in this case, I want you to see how this guy, do you see how this H3O thing right here? This H3O starts here and it's going to end there. Got it? So between here, H3O and H2O, it is down one hydrogen. You get that? I want you to see that. That's why this thing we're going to call a Bronsted-Lowry acid. Now we call it a Bronsted-Lowry acid because it's a system at equilibrium. And we can only use this method when we have a system at equilibrium. You guys get what I'm saying? So it's not an Arrhenius acid. That's when it's a one-way reaction. This is Bronsted-Lowry acid because it is giving up, it is donating, it is losing, and it ends up with one less hydrogen ion. Now, on the other end of the spectrum, you have this OH right here, right? Starts out as an OH, and on the product side, now it's got two hydrogens. So it has absorbed, gained, gathered, taken on a hydrogen ion. Does that make sense? It ended up with one more. So because this guy, the H3O, has lost a hydrogen, this is a Bronsted-Lowry acid. Because this guy has absorbed a hydrogen, we call it the Bronsted-Lowry base. Are you guys with me on that one? Hope so. If not, that's okay. It'll make it a lot more clear. So what that sets us up for is this thing. Ooh, sorry, let's start here. It gives us this idea of a conjugate acid-base pair, right? So here's the deal. The conjugate acid-base pair are two different substances that differ by one proton. It's the only difference. Okay? And so instead of like just staying here, let's go look at an example, which is what this is. So here we see that the HNO3 you think you got everything covered, and then you see this kind of silliness. There, it's a system in equilibrium there. Yeah, it's a system in equilibrium, okay? So there, we got our system in equilibrium there. Now this HNO3, right? This guy turns into, like on this side, this HNO3, it doesn't turn into the H3O, it turns into this guy over here, the NO3. And in doing so, it loses a hydrogen, so we call this the acid. Now watch, this is why we're going to call this other one the conjugate base. Now conjugate can only be over here on the product side. And we're calling it conjugate because it's on the product side. And we're going to call it a base because in this case, when this reverse reaction happens, this NO3 turns back into HNO3 and in the process absorbs a hydrogen, acting just like a base, because that's what bases do. They absorb a hydrogen. So can you see how this dude over here, the NO3, absorbs a hydrogen to turn into HNO3, right? It's because it starts with no hydrogens, it ends up with one more. Now this guy, this is the acid, because in the forward reaction it loses, and this is the conjugate base, because in the reverse reaction it gains. You guys get what I'm saying? So it's these two things that are bouncing like back and forth and back and forth and back and forth in their system at equilibrium. And the only difference between these two things is one hydrogen. So that's what makes these two things the conjugate acid-base pair. Yeah? I hope that was clear as mud. Now, same thing, only like completely like different is you see this H2O right here? Now this H2O turns into the H3O. So going that way, this thing acts just like a base because it starts with two hydrogens, it ends with three, therefore the H2O has absorbed a hydrogen and it turned into the H3O. That makes the H2O, in this case, it's acting just like a base because it's absorbing or taking in a hydrogen. Now, when that thing starts going in the opposite direction, this guy, when it goes in reverse, the H3O gives up a hydrogen and turns back into H2O, making H3O conjugate acid. In this case, conjugate because it's in the product side of the way that I have to write my like reversible reaction, and acid because it is giving up a hydrogen ion. It is donating a hydrogen ion. It is losing a hydrogen ion. Whatever word you want to use. And trust me, the reasons are going to come up with a million different ways to say gain or lose. It's stupid. But if you're confused, you can always ask. So there you go. And these two, the H2O and H3O, these two things are different only by one hydrogen. You got it? So let's go back to this. Here, let me kill this here for a sec. The conjugate acid-base pairs, these are two things that are different only by one hydrogen, right? That is the only difference. And we call them an acid-base pair because on this side, it's going to act as an acid, and on this side, it's going to act as a base. Conjugate base, conjugate meaning that it's on the like reactant side, right? And this thing right here, this thing is going to act like a base over here, and then this thing over here, when it does the reverse, it's going to act like an acid. So these two are conjugate acid-base pairs. You see how that works? This all happened because this, and pretend that's an equilibrium sign. Man, that just chapped my cheeks right there. Remember, this is a system at equilibrium, and it only works with things that are equilibrium because we have stuff like doing one thing this way, and it does the exact opposite this way. So if it's an acid going that way, it's going to be a base going that way. You guys get what I'm saying? And people were like, well, is HNO3 an acid or a base? I don't know, because over here it's an acid, over here it's a base. And then they were like, yeah, so let's call that an acid. Let's call that a base. But we'll just call it a conjugate base because it means it's on the product side. Done. That was so easy, right? So easy. Let's practice. Here we go. Let's do it. All right, let me get out my little pen thingy here. What kind of color do you guys want to do? Let's do something new. Red and blue don't work. Let's do, I don't even know what color that is. Someone artsy fartsy. You're going to have to help me out on that one. You know who I'm looking at. All right, so NH4, I actually have an equilibrium sign there, so yay for me. It looks like the NH4 is going to turn into NH3. So this is the way I do it. Remember, my eyeballs are not my friend. So these are all the ways that I have of, like, you know, cheating the system. I always draw lines like this. What's pretty? Making my conjugate acid-base pairs. You know what I mean? So this is my conjugate acid-base pair. I don't know which is which yet. I just know that these two things are different by one hydrogen. Therefore, they are matched. And let's do, these two are my conjugate acid-base pair because they are different by one hydrogen. Right. And now we got to ask ourselves a question. NH4 turns into NH3, and when it does so, is this stuff gaining a hydrogen, or does it have to lose a hydrogen to turn into NH3? It has to lose a hydrogen, and so that makes this, that makes this, come here, that makes this an acid. You guys understand? So this is the acid, and that makes this the conjugate base, which kind of makes sense because when the NH3 goes backwards, it's gaining, it's gobbling up a hydrogen, right? So in order for this, the NH3 to turn into NH4, NH3 must absorb a hydrogen, making it a base. And because it's on the product side, we're going to call it conjugate. You dig? So this should make these next two pretty easy, right? The OH, and it's just like what goes on my head. Does OH, the hydroxide, does it gain or lose a hydrogen to turn into H2O? It looks as though this thing needs to gain a hydrogen. It needs to absorb a hydrogen. So anything that absorbs a hydrogen, according when it said equilibrium, that has to be a base. Nice. And this H2O has to lose a hydrogen in order to turn into the hydroxide. So this all looks like it's going to work out well. There's my conjugate acid. Acid on the reactant side, conjugate base on the product side, base on the reactant side, conjugate acid on the product side. If you notice, on the reactant side, you have both an acid and a base. And on the product side, you have a conjugate base and a conjugate acid. Can't have one without the other. Dig? Let's move on. Let's do this one. All right, let's get out the handy dandy pen. Thing that doesn't really stick around very much. Let's go with random color palette, this one. All right, what does HBr, hydrogen bromide, what does that look like it turns into? Well, my options are H3O. I don't think something with bromine is going to turn into H3O because that magically disappears bromine. That's silly. So my other option is just Br. So it looks like these two things are an option. Yeah. Let's go random color generator. And then that means my water, my H2O, is going to... I don't even know if that's even a color, but there it is. My water is going to turn into H3O. So now we got to ask ourselves, let's go back. Yep. These two things are different by one hydrogen. Therefore, they are a conjugate acid-base pair. These two things are different by one hydrogen. These two things are different by one hydrogen. Therefore, they are a conjugate acid-base pair. So let's see who's the acid, who's the base, man. Let's check it out. HBr turns into Br. The only way it can do that is if it loses a hydrogen. So this has to be an acid. I certainly hope it is. I'm going to look silly. Yep, it's an acid. So we know if that's the acid, then the Br over here has to be the conjugate base. Never doubt this stew. It's the bow tie that makes it. It's so freaking fly, man. I ain't scared. Rona tried. Couldn't do it. Here's acid and bases. But anyway, back to the good old H2O. Our H2O, let's check it out. Its conjugate acid base pair is H2O and H3O. So this H2O, it looks like it needs to absorb or take in a hydrogen in order to turn into the H3O, which would make this a base. Which is great because it complements our acid base, has to be on that side. And if this is the base, that'll have to be the conjugate acid, right? Conjugate because it's on the product side. Acid because as it goes from H3O over to H2O, it's got to like give up a hydrogen, right? Give it up, right? Awesome. Let's keep going. And how many more of these do we got? I go all day. I don't care. All right, let's do it. Random color generator, choose. CO3 with a 2-, it's aqueous. Of my choices here, it seems like this is my option. So let's make these two. Let's make these two things together. And then I'm gonna go another random color generator. Close my eyes, swirl random. H2O definitely looks like it's got the same one. I'm gonna go to OH, right? So let's just double check, make sure I got my conjugate acid base pairs lined up. CO3, HCO3. That seems reasonable because they're different by 1 hydrogen. H2O, OH, conjugate acid base pair because they're different by 1 hydrogen. All right, I like that. So let's identify. The CO3 turns into HCO3, so that means it has to absorb or take in, add, absorb, uptake. Well, you can use your imagination. It's got to gain a hydrogen. So if this guy right here, the CO3, if that is absorbing hydrogens, do you remember what we call that? If something that absorbs a hydrogen? You're right, it's a base. And so if my CO3 is the base in the forward reaction, you see how that HCO3 has to act like an acid in the reverse because it's giving up that hydrogen, but because it's on the product side, it is a conjugate acid. You dig how that works? And the way this works, guys, I don't know if you've picked up on this, I choose 1 conjugate acid base pair first, right? Preferably the one that's easy to do. Because if one, like on my reactant side, if one is the base, well then the other has to be the acid, right? On the reactant side. And on the product side, once I know which one is the conjugate acid, I know which one is going to be the conjugate base. I'm going to have to go through it, man, because if you do one right, the rest just fall into place. You guys get what I'm saying? Pick it up what I'm putting down there. Feeling flow, ride wave, digging the groove. You smell what I stepped in? I hope not, because that dog is a big dog. She's not a puppy anymore. Don't smell that. That right there. That is just for you guys. In your homework packet, the Arrhenius theory and Bronsted-Lowry theory homework, multiple choice. These are all from the sorry, these are all from your from old Regents exams. You know how this thing do. Man, do these. I think I included the answer sheet. If not, I will be uploading answer keys. You know how to do this, guys. I need you guys to dig into these. Do them like without the answer key. Don't even look at the answer key. Just do them. It's open notes. Man, you can even ask each other what you think the answers are. We're actually maybe not right at first, maybe afterwards. But do it first without, you can use your notes, but don't look at the answer key. Don't ask for your friends for help. Then go back and ask questions after you check like what's right and what's wrong. Because that's where you need to spend your time. It helps us figure out what we do and don't need to study. Because if you got like half of them right, why would you spend your time studying that? Because you already know it. You go to the ones that are wrong, spend your time there. Way more effective use of your time. And I'm done, guys. I am spent. Yeah, my kids have it. My whole family has it. But listen, also, before I sign off, I just want to tell you guys one more time, please. I have no idea how we got it in this house. We were psycho. We wiped down our mail with bleach before we let it into our house. Wash your hands. Please wash your hands. And the social distancing thing is a kind of a real thing. If this hits people who are slightly less, I don't know, lucky as I am, this one was ugly, man. But I'm good now, and I'm collecting homework. I deserve this one. All right, guys, see you later.